And today is Wednesday, April 16th, and we welcome John Kutsch to tell us about thorium and all the latest news, but also a lot of the basics and understanding how what role thorium will play in the energy future.
Hey, thanks for having me. Um, I'll share a screen in a minute here. I apologize for the delay in logging in. Zoom always, picks as you're logging in to tell you that you have to, upgrade or whatever. So whatever, that's the nature of what we're living with these days. Uh, Here, I'll move that a little bit. The so the give you a little bit of a background uh, for myself. The I had a client. I still have the client, but I had a client about 16, 17 years ago, and he was, he was a very forward-thinking fella, and he was kind of asking for if we could find some replacement metals for him, and he was going through the. He was he was like, "Hey, will tin work?" And then we'd do some research for my engineering company, and we'd be like, no, he's like, would iridium work? And we're like, well, it might, but it's not quite, and it's super expensive. And eventually realized he's just going through the periodic table. He wasn't he wasn't doing anything to clever or anything like that. He was just literally just running his finger across the periodic table. But eventually he got to thorium, and he said, would thorium work? And I was like, I don't know. I've never heard of this stuff. And so we sort of did a relatively deep dive on it. And, it was a fascinating story. It's the third nuclear fuel. It's over the last 150 years, it's had thousands of industrial uses, alloys and ceramics and things like that. We was just, it was, but basically it was being forced out of the market. And, so I reported back to him, you know, he's like, so will this do what I want it to do? And I said, no, but it's basically just mining waste these days. It's just side stream byproduct garbage. He's like, oh well. And I said, but it could save the world. And he's like, what? How can garbage save the world? and and I said, well, it's because it's this incredible missed opportunity. And it all comes down to the fact that thorium was misclassified back in 1954 Atomic Energy Act. It is in fact one of the three nuclear fuels. That's uranium, plutonium, and thorium. And obviously, there's other fuels like spent nuclear fuel that can be reburned and reprocessed and rebred. But in terms of the naturally occurring nuclear fuels, it's thorium, uranium, and plutonium. But the one of these is not like the other, in that the uranium and plutonium are fissile, meaning if you get enough of them in one spot, they will start to fission and react and get really smoky and weird. Whereas you could put millions of kilograms of thorium, on a giant stack, and nothing's going to happen because it's fertile. So it can't react on its own. It needs a neutron source in order to fission. And as soon as you take that neutron source away, it will stop fissioning. Um, it's very interesting material. It's a mild alpha emitter. It obviously emits other elements too, beta and gamma, but almost about a billionth as much as naturally occurring uranium would. We have thorium is completely usable in terms of a fuel. It's completely usable as is. There's no such thing as highly enriched thorium. So therefore, there's probably about times more thorium in the Earth's crust than there is uranium. And in you probably understand that only about 0.3% of most uranium ore is usable as U-235. So when you put together in terms of usable thorium versus usable uranium, there's 2,000 times more thorium available to us on planet Earth. You know, that's a that basically equates to tens of thousands of years of nuclear fuel for the entire planet, for the entire energy needs of the planet. The 4 exajoules of energy that we use. That's not just electricity, that's liquids also. So thorium really could save us, if we chose to. The Chinese are obviously very far down the path of developing thorium fuel, specifically for a thorium reactor system called the LF1, the uh, liquid fuel one, actually. And and the West is not very far along in it at all. so so this is where I have to quiz the crowd. How many of you? I'm probably wandering over a footpath that many of you have walked down. Ray, how many of you are already familiar with things like molten salt reactors and some of the nuclear fuel issues I've been talking about? I'm assuming, yeah. So the rest of you just no reaction. I'm getting a reaction from Les, and I know David is obviously very familiar with it, but no one. Okay, the rest of you guys. So okay, there's you know, just give you like a microscopic background. The uh, fuel wise, and this is the last I'll speak about thorium in terms of its fuel characteristics. Back in the 1940s, when they discovered that thorium could be a nuclear fuel, that it could it, once you activated it with a neutron, it would be a net giver of neutrons. It's sort of like starting a campfire. Wood won't, big pile, a cord of wood in your backyard isn't going to just burst into flame one day. You need to start it with some kindling and a match of some sort. And that's how all thorium fission has to be done. So thorium is just a fuel. People conflate it with the molten salt, uh, but it's most successfully actually been used in solid fuel reactors. The shipping port in Pennsylvania was the first commercial nuclear reactor, and its last load of fuel was thorium uranium MOX. Ran successfully for about 5 years on the fuel. And when they when they decommissioned the reactor and pulled the fuel bundles out, uh, it was proved the miracle of breeding existed. There was about 1.4% more fuel than when they started. So it's one of these amazing ideas that we can breed fuel, then burn it in a fission reaction, and then breed it in a breeder reaction, and we can close the cycle. We can talk about uh, how the Russians have closed the cycle later, if you want to hit on that. But so more,
I want to say,
so
just
there's a yes,
put in
sir.
one thing. From Thomas Pedersen's TED Talk, I learned that your entire life's individual life supply of thorium would be about the size of a golf ball for
Yep.
every person on Earth for your entire life, and that includes running all of society.
Oh yeah, yeah. So a 60 millimeter ball of metallic thorium would have, if somebody gave that to you as a baby, and that would easily satisfy all the energy you would use in your entire life. All the liquid energy you used, all the electric energy, all the all your share of the thermal energy used to make cement and things like that. Yeah, it's a phenomenally energy dense. It's about it's about 6.5 million times more energy dense than coal. So that's a 60 millimeter ball of thorium would weigh about uh, I think it's about 10 pounds. so it's a little ball, but it weighs. It's true. The SG on it is tremendous. I think it's 5 times the gravity. 5 times water. And so it's a tremendous. Um, that and the energy density is tremendous, and the fact that it sort of as you it's it as I just mentioned, it sort of is a natural breeder because of the natural cycle that thorium wants to go through, whether it's in solid fuel or liquid fuel. Is it starts out as thorium 232, gets hit with a neutron, becomes thorium 233, gets all excited and just transmogrifies into uranium 233. Uranium 233 is incredibly unstable, and so it almost instantaneously self fissions, splitting off two neutrons. And when it fissions, it turns back into thorium 232. And so it's called the pure cycle when you do it that way, because there's no weird actinides coming off of that. Obviously, daughter products, uh, you know, um, basically appear uh, no matter what you do, but you're talking about 1,000th the amount of waste profile than like a uranium light water fuel rod, which is especially shameful use of energy because 95% of all the energy in a uranium fuel rod for a modern light water reactor is left in it. We only use a fuel rod for about 18 months, maybe 30, maybe 36 months, and then we throw it away. we throw it away as soon as we suspect that cracks in the cladding appear. So that circles us back to the molten salt, and the molten type reactors, things like lead, sodium, stuff like that. The molten salt is unique among them in that the actual fuel and the coolant are the same thing, and because of that, you get because it's liquid chemistry, and because the salt can't flash, the salt can't boil. You're not going to have a steam explosion with the salt. The salt operates at a very high temperature of around 600 degrees Celsius, which makes it a much more efficient generator of things like electricity or even thermal process heat. The salt is an ionic molecule, which means it's infinite in terms of being able to accept radiation damage. You can't damage it. So once you make it, it's good forever.
John, do
So
you have
as you
a diagram, or can you just explain the mechanics of the cycle in producing heat for or electricity?
uh, Yeah, give me a minute, and I'll try and pull up the standard,
Yeah.
Idaho
Okay.
illustration. But I don't want to make you guys watch me, paw through my file directory. But suffice it to say that these are the characteristics of a molten salt that make it attractive, and that's why you read about it and hear about it. The inherent safety is what basically it comes down to. But to me, the safety is great, but you get a huge increase in efficiency in terms of process heat and electricity generation. You get a huge you can essentially burn up 90 to 95% of the energy instead of just 5% of the energy in the thorium. Any waste created is in the liquid. So some pretty straightforward chemistry like vacuum distillation, inline filtering, can filter it so that all the neutron poisons can be taken out pretty quick, and therefore the I call molten salt fuel. It's like sourdough bread. You know, you use it and use it and use it until your reactor is used up, but then you transfer the salt to the next reactor, like a, like a sourdough starter. You add some new salt to it to, clean it up a little bit, and off to the races you go. And you essentially the fuel salt is has an infinite life. So that's what attracted me back then. That's what inspired me and lots of other guys to start Thorium Energy Alliance and start to revive this technology. But um, we'll set that aside for a minute. Hopefully I've convinced you that thorium is an excellent fuel, and but where does it, is what we're most concerned about at Thorium Energy Alliance is essentially you could sum it up as like where does thorium come from and how do you use it? And so I'll share a screen with you real quick here. Screen two, share. Well, hopefully the screen's being shared with you folks now. Can you see this screen? Yeah, okay. Get a little okay sign here. This new version of Zoom is an unpleasant iteration. You guys are in like a little tiny column of itty bitty videos, and my screen's way over there. Well, anywho, uh, so this is what should make a huge matter in your life, even if you're like, God, I hate this nuclear stuff. I hate the idea of thorium. I don't like nuclear reactors because they freak me out. Well, you're going to have to, like, if you don't like it, we're going to at least have to deal with it, because what I found out, a long time ago when I asked about thorium was, where do you get thorium? Well, you get it from rare earths, right? So rare earth minerals and thorium just love each other, and they bind themselves together in a thing called a phosphate rock. So you got monazite, xenotime, basicite, apatite. You got and monazite, of course. If I didn't say that, the those are your major phosphate minerals, and we mine those minerals today in the USA for the phosphate, for the fertilizer, right? And then we throw everything else away. And why do we throw it away? Right now China's embargoing rare earths. Don't we have rare earths? Yeah, we got more rare earths than anyone in the world. We got hugely more rare earths than China. You know, Brazil and India have huge amounts of rare earths that they never tap into. Australia has vast amounts of rare earths that they never tap into. And you have to ask yourself, well, why is that? Well, it's because in 1980, uh, uh, a weird bedfellows situation, the Carter administration and the Reagan administration basically worked to pass incredibly onerous rules with nuclear materials. And um, and if you ever, if you ask yourself, we just released a video last night about this. You know, in the 1970s, we got CAT scans, smoke detectors, food irradiation. We got this handful of monumental achievements of technology. Cheap cheap smoke detectors for every home that saved millions of lives, CAT scans that have saved millions of lives, food irradiation and medicine irradiation that saved millions of lives. eliminated listeria and other foodborne pathogens in Europe. Not so much in the United States because we're weird, but that was all in the 70s and nothing since. Well, the nothing since is because we've saddled working with nuclear materials with huge burdens, far outweighing the risk profile and the benefits. When, so there's a radioactive component to a smoke detector. Are you willing to go throughout your house and throw out all your smoke detectors because there's this vanishingly small amount of americium in them that cause an ionizing radiation stream that helps it detect smoke? Of course you're not going to do that. Are you going to turn down a CAT scan when you're in the hospital suffering from a tumor or some broken? No, you're not going to turn down a CAT scan. It's going to save your life, but it's going to expose you to a pretty decent shot of radiation. So, the idea that we can't handle this zero limit of radiation destroyed the critical materials market in the West. There used to be a huge company called Rhodia in France that made about 60% of all the rare earths in the world. There used to be Dow and uh, other companies in the United States. I'm blanking on who the big ones were, but before 1990, 99% of all the rare earths in the world were made in the United States and France and Japan. And then within a few years, the tables had turned. It became so onerous to work with radioactive anything that, and China, leapt up out of its chair and said, we'll work with rare earths. and so they became the 100% monopoly supplier of rare earths to the rest of the world. And for years, we thought, oh, that's great. We'll let these stupid Chinamen deal with this filthy, metal separation process, with all the acids and everything that you need. And, they took over this market, and the entire world rare earth market is only about $4 billion. It's tiny, but China's leveraged $4 billion worth of rare earths into $7 trillion of manufacturing. Because if you want to make something with a magnet, especially a high performance magnet like a neodymium iron nickel boron magnet or a samarium cobalt magnet, you have to make it in China. So, it's like controlling yeast. Yeast has no value to it. It's in the air. You breathe it around. You leave some, you porridge out, and you'll get, like primitive bread. So like, but if you could control yeast, you could control the production of penicillin and beer and bread and all sorts of other, fermented products. You know, rare earths are the yeast of industry today. And the only place to get that yeast is China. And so it's become our mission at Thorium Energy Alliance is to break this terrible policy chain and bring critical materials refining back to the West. Particularly, we're working, as you can see up there, Caldera Mining, who's in Missouri. So I'll just, hopefully you can see my mouse there. I'll just run through very quickly um, how we make critical metals. Most people don't understand where anything comes from. Where does food come from? The supermarket. Where does electricity come from? That switch on the wall. And they sure as hell don't understand where these critical materials and magnets come from. And it's a very complex process. It's not like iron where you just dig it out of the ground and melt it, and voila, you got iron. You know, this is a hugely complex process, and you'll quickly understand, the thorium connection. So, in the start here, you do in fact, dig this phosphate material out of the ground, and when you dig it out of the ground, you crush it into baby powder, 2 micron dust. Then you that's the mechanical cleaning process, and then you separate out things like silica and calcium and other gang material that you don't want as much as you can, and then you put it in a digester full of your acid of your choice: hydrochloric acid, nitric acid, uh, you know, and you have to melt it down into like a goo, a slurry, and then you take that separated slurry, that cleaned up slurry. Now you've got what's known as a rare earth um, mixed oxide concentrate, and you put that concentrate into the separation cycle. The separation cycle these days, using primitive, World War II era chemistry, it's an SX exchange system, and you put it into a tank, and then you flow it in from tank to tank. You have a farm of tanks, 1,500 tanks, and these are all settling tanks, and there's special organic ligands, like that grab on selectively to different materials, and to separate out the rare earths, the 16 available rare earths. You've got to pass this material for months through these tanks over and over and over again. 3,000 passes minimum just to get things like the light rare earths like neodymium, praseodymium, and then the exotic hardcore ones like homium. These, it could take 30,000 passes through these tanks, through these settling to drop out this material. So it's hugely expensive, time consuming, and you're not using the friendliest of chemicals. And at that point, you have separated metals or separated oxides, and those oxides then have to be put into a special vacuum furnace using helium cover gas, in completely airtight situations, because this stuff reacts like sodium. You can't let the rare earths touch air, or else they'll just flash into dust in a very violent manner, just like sodium. You've seen sodium thrown into water, it explodes. Rare earths are that reactive too. So to make them into metal, you have to use these very exotic furnaces that are only available in China these days. We haven't made them in years in the West. Uh, and then once you get the metal, you have to transfer them under cover gas, and you put them at the bottom of a jar of oil to preserve them, or you vacuum seal them into very thick glass jars. And then those can finally be turned into magnets for fighter aircraft, nuclear magnetic resonance machines, the airbuds in your air, your earphones, the speakers in your television, the seat control motors in your car, and the electric motors in your Tesla, or the electric generator in your power station or your windmill. So that's pretty involved. What you see there in the separations going through those, this is the step that matters. This is the step that kills the industry in the United States. Uh, we 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 can't, in the United States right now. There's one company that creates rare earths supposedly, but all they can do is clean it up, and digest it a little bit and make a paste, and then they sell it to China. Because if they get to this point, they're going to drop out thorium and uranium, a little bit of uranium, mostly thorium. And our solution is that we get into that step. We have a thing called the Thorium Products Corporation, It's a real corporation. It's a Delaware corporation. Uh, you know, we're looking for uh, we're looking for funding right now from the United States government. Is you know, we're in negotiations right now with the Department of Defense, who has suddenly become very desperate for these solutions. So the Thorium Bank takes this side stream byproduct, and the rare earth facility delivers us the side stream byproduct of concentrated thorium, uranium, you know, slurry. And then we take it, we turn it into thorium tetrafluoride for use by companies as a nuclear fuel component, thorium oxide for use as a mixed oxide nuclear fuel for solid fuel companies like Clean Core Thorium Energy here in Chicago. And then we make thorium nitrate for people that need to make thorium uh, uh, products like X-ray tubes and things like that. And then we refine all the way to a thorium metallic product, and then we store it in refrigerated room. We monitor to see if it ever develops like a little bit of radon or anything like that. And so we take it from being a side stream product of waste and turn it into hugely beneficial materials up here. And I don't know if this is readable on your screen. I could try and zoom in. You know, this new version doesn't let you manipulate the thing too much. But suffice it to say, currently today you can still buy 4% thoriated welding rods because thorium, uh, one of its great characteristics, well, let me just say the characteristics of thorium are that it's a huge fat atom, so it's very, very willing to give up its electrons. It also acts like a refractory material in that it's the highest melt temp metal. It acts as a platinum group metal in that it's a hugely catalytic material. So it's a very funny material. It acts as a rare earth. It's just below cerium in the periodic table. And because of that, you can make the clearest optics in the world, the highest temperature ceramics, thoria in the world. You can make these welding rods, and why are they so good? Because these welding rods are the only rods that are able to sustain a spark in high nickel alloys. Dow and W.R. Grace have hired us to source thorium so that they can revive their thorium catalysts, which they use to take natural gas and turn it into ethylene plastics. Uh, Curio, Copenhagen Atomics, and Clean Core Thorium Energy have offtake agreements from us for the actual fuel, so the thorium tetrafluoride and the thorium oxide. And one of the hugely interesting aspects of thorium is that it makes things much more conductive, like the welding rod. So if you take that and extrapolate it, we can add about 1 or 2% thorium. So we've got ARPA-E funding, Department of Energy funding to pursue this. We can add about 1 to 2% thorium to aluminum, and we can make it as conductive as copper. Now you might know that we're about an inch away from running out of economic copper on planet Earth, right? We're just used up all the easily gotten copper, and there's no new copper mines coming online anytime soon. So how are we going to get all these new transmission lines we want? How are we going to electrify the Earth? All this stuff. Well, you're not. You're certainly not going to do it the way they are now, but you could stand a chance of doing it if you did something like thoriate aluminum and made it as conductive as copper. We got a lot more we got a lot more aluminum, and you know, we could vastly extend the availability and uses of copper and thorium. Thoriated aluminum is cheaper than copper. It's lighter, so it's easier to work with. It's got a huge amount of interesting applications. Probably most interesting to us is the cable industry. So taking transmission cables and thoriating them, and instead of using copper cores, we would use aluminum cores. So they'd be cheaper, lighter, easier to work with, stronger. So it's a win-win-win. And anyone who's like, well, they're radioactive. Well, last time I checked, if somebody stole a transmission cable, it'd be pretty obvious that it went missing. Every foot of the transmission cable would have little traceable chips embedded in it and QR codes. And, you know, we chose transmission cables because of their very, very high impact, but also their very high traceability. Uh, that's just probably the most prominent uh, project we're working on right now in terms of thorium. But the microwave in your house, when you heat up your coffee, you're heating it up with a thoriated magnetron. So we still have uses for thorium today outside of nuclear fuel. uh, Hugely important uses could be brought back, like magthor, which is magnesium thorium alloy used in all the Gemini and early Apollo spacecraft. All the 1960s era fighter jets like the Phantom used magthor. Thorchrome is one of the highest temperature possible heating element materials you could imagine. Uh, Alumathor, which we just spoke about for transmission cables and other electrical transmission. You could thoriate copper. So thoriated copper transmits electricity as well as silver does. So, the effect that you see aluminum to copper, you can see the copper to silver effect. So that should be extraordinarily exciting to you. And if nothing else, uh, you know, very self-serving for you would be the advent of actinium-225, which is derived from, you can milk thorium, which is a process by which you irradiate the thorium with a neutron source, and then you purposely make it create daughter products of actinium-225 and bismuth-218. And actinium-225 has had a 100% success rate in curing metastatic prostate cancer. It's got a huge success rate. It's the most successful nuclear medicine. And that's why Bill Gates's TerraPower, Shine Medical, um, Materials Corporation, there's about uh, 5 companies right now in the West developing actinium milking processes from thorium. Now that uses a vanishingly small amount of thorium, like a kilogram, a year would be a huge amount for them. But it shows you the unbelievable properties of this material and why we shouldn't be afraid of it, why we should do everything we can to, utilize it. We were given this incredible gift and we've shunned it for 50 years. The the little parable that I leave my last conference with was, you know I'm not a really religious guy at all, but I do, I was raised Catholic and I remember the stories. And you know we've taken this phosphate rock, this rare earth bearing, thorium bearing phosphate rock, and we've thrown it away. We've rejected it because we just didn't like it, and we've turned it down. And so just like the story in the Bible, we, you know, the builders rejected the stone that the builders rejected have now become the cornerstone. Nothing is more valuable now in this world than phosphate mineral rocks. You know, we need, and you could even start to speculate like who made this rock, because this rock contains all the fertilizer we need. This rock contains all the exotic rare earth materials that we need. And this rock also contains all the energy metal we need in the form of thorium to lead a future and live life on this earth, an earth that's about to have about 10 billion people on it. So, you know, the stone that was rejected has become the cornerstone, and we see that now. And hopefully, Thorium Energy Alliance can be a big part of, uh, big part of uh, making it become, uh, more and more accepted and beneficial to society. That's my little primer on thorium and its many uses. Uh, I I'm available to answer questions for as long as you care to ask them.
I'm just going to do the first one. So it's my understanding that it's the Department of Defense that is blocking really the extraction and processing of thorium in the United States. Is that right?
No, I wouldn't say it's the Department of Defense per se. I'd say it's NRC, Department of Energy. That
Oh,
yeah. So it's forgive me
so
here.
then Chris Wright should be able to make some progress there.
Oh yes, from your mouth to Chris Wright's God's ears. Like
What are you saying that he's not spending any time on it? He's opposed to it?
no,
Well,
no, no. He's a board member of Oklo Nuclear. He's a very interesting fella. He made his money in fracking, but he's invested heavily in geothermal. He's obviously invested very heavy in advanced nuclear. So he's clearly a believer in it. He I we met with him a couple times over the years, before he was ever like a glimmer in the Department of Energy's eye. He was just pretty well known energy executive, and his philosophy was like we need more energy, to lift up humanity, is basically is which is not not wrong. And he believes in nuclear, as part of that lifting up of humanity and presenting opportunities and things like that. So yeah, we're obviously very actively trying to work with his people to reclassify thorium, put its, that would be the number. If somebody held a gun to my head and say, you one change, you can only get one change, and I'd say reclassify thorium, put it in its own category, because uranium and plutonium, you can only do essentially two things with them: make energy and make weapons. There really aren't other uses for them. Whereas thorium, you can make energy and you can make 1,000 other products with it. And it's a fertile, it's not fissile. That's the demarcation. It's a fuel, fine, keep that as its classification, but it's a fertile fuel, not fissile. And that's the easiest way to make the distinction. For the regulator to adopt that would take almost nothing, and it would make a huge difference in how we have to treat thorium. Right now we have to treat it as if it's weapon material, with 1,000-foot setbacks and mean dogs and guys walking around with big heavy weapons, you know and instead we could treat it as a normal material, like hydrofluoric acid, right? 3M uses millions of gallons of hydrofluoric acid every year. You can't imagine a more dangerous material, but it's a bone eater. If you get some on your skin, it goes right through your skin and eats your bones. And, but they're able to work with millions of gallons of stuff a year in a civilian environment, near cities, delivered on train rails and public roads. I mean, it's vastly more dangerous than any thorium would ever be. So I mean, it's just we could we could treat thorium as a normal commercial material with a certain low level hazard profile that's easily mitigated. So changing its classification would mean everything, and there's a whole host of little other policy changes that would enable. And if all we did if all we did was change the policy so that we could just store thorium for some other future smarter generation, they would put a bronze statue of us in the park, because we would enable, all the neodymium and praseodymium and holmium, all the critical materials of rare earths, the cobalt locked up in the phosphate materials. We're desperate for cobalt. All the other materials that are locked up in rare earth bearing phosphate minerals would finally become available to us if you just let us become the world's thorium garbage men. We'll take your garbage happily and store it until some generation in the future understands the huge gift that thorium is.
And tell us the concept of the strategic reserve.
Well, the strategic reserve was that little box down in the lower right hand corner. It's as simple as it's just a big box with barrels of thorium paste, and the barrels are refrigerated. It's a real belts and suspenders. It's kind of silly. It's seismically damped. It's refrigerated. There's an insane amount of radon detectors, because one of the daughter products of natural thorium is radon. So it'll, uh, 10 million pounds of thorium paste would create some de minimis amount of radon. So we would the whole point is we're trying to tell the Department of Energy and the NRC through our licensing process. We're still we're still in the licensing process to get our thorium bank. um we just said, hey, we basically wanted to show them, like, we're going to go over the top to store this material. It's in the Chinese store their thorium paste in basically burlap sacks in little metal Morton buildings. you know it's because they know it's inert. But we went over the top. But the thorium bank is simply just a warehouse built inside a warehouse with a lot of monitoring, so that we can store all the offtake byproduct, rare earth refinement line.
And
That's all.
the
It's
point is to allow production of rare earth everywhere for all those
Yeah,
upstream products, and then to hold it for future changes in regulation and uses at some point
yeah,
later.
yes,
And
sir. I mean,
it's
obviously.
essentially a nonprofit. Is that all
Oh
right?
yeah. Well, the way we're set up right now. We're a Delaware corporation. We're a public benefits corporation, and so that means we essentially act sort of like a utility. We do one very narrow scope of things. Uh, we make we make a very narrow scope of products: thorium tetrafluoride, thorium oxide, thorium nitrate, and thorium metal. We sell off the uranium. We sell fluoride uh, into the integrated circuit um, production market. Um, and there's some other uses there's obviously a lot of uses for fluoride, but our main goal is to support the integrated circuit market because of the nature of our fluoride. And that's it. We don't make a profit per se. Uh, we act very much like an electric utility or a water utility. We're there to provide the materials so that others can make valuable products from the materials that we can provide them. So it's called a public benefits corporation. It's sort of like a triple bottom line corporation. We can sell stock, we can be publicly traded, but we also get the benefit of having being very similar to a nonprofit. So it's a hybrid sort of corporate structure.
But you haven't been allowed to do any or very much.
Well, we're about depending on when you start the clock, we're about year 3 or 5 into getting our thorium license. We've used a lot of consultants. We've spent a couple $1 million, and
Mhm.
we've just now uh, got our final engagement letter with the NRC and been assigned the reviewers. They because it's because we haven't made thorium in this country for 55 years. Essentially, I mean, there's some exceptions to that, like Dow made thorium catalysts down in southern Illinois up until the late 90s. But effectively, we haven't refined thorium in this country in a long time. And so the NRC literally doesn't know how to give us a license. So right now they're debating as to how to regulate us. And we're basically asking them to go back into the past and just say, well, how did you regulate WR Grace or any of these other companies back in the 70s? Just do it like that. And they're like, oh no, we need to do it to modern standards. So they're wanting to regulate us as if we're a uranium refinery, and we're like, absolutely not. That goes back to the nature of the material. We're like, we are not anything like uranium. We don't have any of the issues that uranium has. We will fight you tooth and nail. You have to regulate us as our own thing. If you want to use uranium as just like a starting point guide to help you understand the major steps of regulating, we have no problem with that. But the level, they call uh, I believe it's called highest most critical hazard material, and that's absolutely the opposite of what we're trying to do. We're we're trying to say we are absolutely not a hazardous material, and we are absolutely not critical. Critical in the sense that we cannot become a critical state by ourselves. It's a fertile material. It's not fissile. So so you can appreciate our frustrations.
Could you make a bomb out of it if you wanted to, if you had a lot of it?
My response to this to everybody, I get this a lot, and even like so-called supporters and stuff like that are like, well, you got to watch out for proliferation, and I'm like, all right, show me anybody since 1955 who's tried to make a weapon out of thorium. Right? In 1955, the United States of America made two U-233 bombs. The U-233 was obviously derived from thorium-232 at huge expense. The might of the American industrial complex it took to make this little bit of U-233. It was so phenomenally difficult to work with. They thought they were going to kill the technicians that put the bomb together. They blew one up. It had a shitty uh, uh, load, or it was basically a dud, and they destroyed the second weapon because they were just like, they didn't even want to deal with it. So it took the industrial might of America to build two bombs that sucked, and that was 75 years ago. Nobody in their right mind would ever try and do it. Did Why doesn't Iran do it? Their beaches are covered with monazite. Why did India choose to make, you know, uranium and plutonium weapons when they broke the non-proliferation laws? Why didn't they use thorium? They've literally got the greatest thorium reserves in the world. It was right there. Their beaches are black with thorium. Did they use that? No. Brazil, when Brazil had its nuclear weapons program, they used uranium and plutonium. Their beaches are black with monazite. Why did they use that? No one would even known they were doing it. And they didn't. And on and on. Nobody in the world, could you make a bomb? Yes, with scores of billions of dollars. And here's the other, proliferation resistance aspect of it. I'm pretty sure somebody in the world would notice this huge fucker industrial complex to make these astoundingly bad, unstable weapons, you know. So it's not like you could do this in secret or in a bathtub in your backyard, so no, effectively in real life, you cannot make a weapon from thorium.
Nigel.
I call them blackboard smarty pants. We'll get these professors once in a while who will say, "Oh, here's how," and they'll draw like a little flow chart, how to make it. I'm like, yeah, every step in that flow chart is $5 billion. And yes, sir, Nigel.
Well, yes, thank you so much. I wish I could say that I kept up with the presentation, but it was quite fascinating. Just on that final subject, I don't know if you're familiar with this Pulitzer
Sure, yeah,
Prize book by David Rhodes.
yeah, Richard
Um,
Rhodes.
sorry, Richard Rhodes. Yes, I read it quite some years ago. I wish I'd reread it before your talk. Um, Could you just cover some of the history? Because it's quite fascinating. Obviously, in those days, thorium was fissionable. It just required neutrons working at a much faster rate.
Right.
Um, who was producing the thorium in those days? And, what did it take?
Well, we've been thorium. It's the weirdest story of all. Like Father Berserblius, I always screw up his name, but Father Berserblius in Sweden, found this weird rock while rowing his boat around a lake, and he and this is like 1850, and they discovered that it was a new element, and so he called it Thor, thorium. And so then they were like, well, what are we going to do with this rock? And they suddenly discovered that thorium has huge fluorescing properties, right? For it, when you heat it up, it fluoresces like crazy. So they would take uh, uh, monazite or apatite back in the 1880s and turn it into thorium nitrate and cover gas lantern mantles with it. And so all the streets of America and London were illuminated with thorium gas lantern mantles for 100 years. And finally, obviously the most of the street lights were converted to electricity and stuff over time. But the Boy Scouts still had their little camping lantern. Anywho, the point is, we've been processing thorium for 150 years and putting it to practical uses. Lighting, super high efficiency lighting, was the first major use of thorium. And soon after that, they discovered some of its other properties. Its incredible heat resistance. One of the They made thoria, which was the highest temperature ceramic. So huge amounts of the early semiconductor industry were enabled by the fact that they were able to make these thoria crucibles and do electrical induction on things like gallium and silica and stuff in these ultra high temperature crucibles, and you know kind of a hidden history of thorium in industry. So that's well before World War II. And thorium and thorium nitrate were very readily available. You could buy it in your chemistry shop. And that's when I'm blanking on the guy's name, but General, God darn it. Well, it was during the Manhattan Project. out west in Los Alamos. They were looking for nuclear materials, and that's when uh, uh, I forget the general assigned one kid. He said, "Hey, look at this thorium stuff and tell me if it could be used as a fuel." And the kid sat there and he bombarded it with neutrons, and he saw that there were more neutrons coming out than going in, and voila, there's your nuclear fuel. And so he went back and he said, the general famously said, "You've made a $4 trillion discovery." And so
Was that
I don't
Richard
know if I answered
Feynman?
your question.
Was that
What's that?
Richard Feynman, the student?
No, it wasn't. It wasn't Feynman. Yeah,
Oh,
I'm blanking on and it wasn't General Groves either who assigned it. It
yeah,
was like
Groves,
Little.
the fat guy. Yeah, that wasn't him. Oh,
No, it's like General Littleton. I think it was
ah,
something like that. Anywho, they actually pop up in the Oppenheimer movie.
yeah.
Um, yeah.
Okay, Les.
Yeah, fascinating speech, John. Thank you. Thanks very much indeed. The Chinese, you're implying that they don't have the same regulations holding them back in creating thorium.
Uh-huh.
Do they produce a lot of it? Do they have it available? Have they considered using it for energy?
Oh yeah, man. Oddly enough, they don't have thorium themselves. All their thorium has come from imported uh, phosphate materials.
Hmm.
They what China has uh, for rare earths is stuff called ionic clays, and by some weird by some weird fluke, ionic clays have thorium and uranium in them. Uh, but the way you process them is astoundingly filthy, or at least the way the Chinese process them is just mind bending how filthy they are. But they built two entire cities, Bayan Obo, uh, you know, uh, to process rare earths. So they're very committed to it, and all the thorium, they don't throw it away. They set it aside. Like I said, they take this paste, they fill these like polyester burlap sacks with it. They sew them shut. They stack them on, on pallets, and then they fill these Morton buildings up because they know they've got 100 lifetimes of energy sitting. So they committed billions of dollars to develop thorium fuel cycles. So they have a CANDU reactor that they built with Canada, and the
Hmm.
first fuel that they ran it on was thorium MOX fuel. And I believe I believe it still runs on thorium MOX fuel. They have HG, they have an HTGR, high temperature gas reactor, that runs on a thorium version of a triso fuel.
Hmm.
And then, of course, most important and interesting to me is that they have the thorium molten salt reactor, the LF1, liquid fuel one, and that was specifically designed to run with thorium as its primary fuel element in molten salt. And it's a direct, copy of the molten salt reactor experiment from Oak Ridge back in the 60s. And they have flat out said that, they built LF1. LF1's been running for about 3 years. LF2, they started to build it at the same time. So LF1 is 2 megawatts, LF2 is 20 megawatts, and they're about to start LF2. And at the same time, they started building LF3, which is 200 megawatts. And their philosophy, in the United States, we wet our pants and wring our hands, then we build a reactor, then we run it, then we do an autopsy, and then we decide what the next reactor is going to be. China builds all three reactors at once, and they say whatever we learn from LF1 we'll incorporate into LF2, and whatever we learn from LF1 and LF2 we'll incorporate into LF3, because it's cheap enough for them to tear something out and rebuild it, or restructure it. So they're already going to have LF2 running this year. That's 20 megawatts. And right behind it, they should be not more than 2 or 3 years away from LF3 running. So you're talking about 2029, 2030. Once they get that shaken down and the bugs worked out of it, they have openly said we're gonna give thorium molten salt reactors away to the world. We're gonna give them to Indonesia. We're gonna give them to Brazil. We're gonna give them all over Africa. And if you're a poor country, it's gonna be pretty goddamn hard to turn down free nuclear power. Now the Chinese obviously are gonna run it. They're gonna fuel it. They're not going to teach anybody in a local country how to do anything with it. So the benefits to the local country are one thing: cheap, abundant, 24/7, power. But that's a huge thing. If your country is suffering from energy poverty and China comes along with a modern version of atoms for peace, now not only have they done something that's pretty hard to argue isn't a great thing, they brought cheap, abundant energy to countries like Malaysia, Pakistan, India, but they've also diabolically enslaved those countries to their energy system for the next century at least. So
Doesn't it all
yes,
motivate
China,
you?
that's a long way of answering your question. China is highly committed to sending, and why thorium? Because thorium's non-proliferating. It's the civilian nuclear fuel, right? Glenn Seaborg told John F. Kennedy that back in the 60s, thorium should be the civilian nuclear fuel. And so China feels safe sending that technology around the world because no one's going to steal it and turn it against them.
Doesn't that all motivate your Department of Energy to take thorium more seriously and try to develop themselves?
Well, well, my organization has been gone from having the head of the Department of Energy call us a boatload of fanatics to 2 years ago, they've officially, the policy has been changed to allow funding for thorium. So up until a few years ago, the Department of Energy's official policy was they will not fund anything to do with thorium. And if you asked them why, they say, well, because no one uses it. And the circular logic there is what became evident even to them, that people don't use it because there's no research done on it and they don't know how to use it. It's like, well, why don't they know how to use it? Well, because they don't use it, and so it's like, well, maybe you could break that chain and help do some basic research about how to develop these fuels and these materials. And they finally, the tides turned. We have a lot of supporters now in the DOE and the national labs. And so now there's, not only did they change that policy, not only did they encourage research in thorium, but they've also said, they've budgeted millions, not billions, but, they've budgeted millions of dollars for the deployment of thorium fuels and thorium as a material application. And so has the Navy and DARPA, the Defense Advanced Research, and Air Force and NASA. So the agencies, the agencies are now funding thorium, and they've taken thorium. Not to put too fine a point on it, but they've taken thorium off the shit list. So it was, whenever we feel like we aren't making progress, we have to remind ourselves that we've gone from being called fanatics to now they take our research and our development seriously.
And is the new administration making a big difference there? Was it too early?
Well, as was pointed out, Chris Wright is the Department of Energy head now, and he's obviously hugely influential with what the policy is. Uh, you know, this administration has made some pretty oddball picks for certain things, but Chris Wright was a very stellar choice from any administration. You know, he's the first energy producer to be the head of the Department of Energy. Everyone else was like academics, like Ernie Moniz, or, you know, old politicians like Perry. You know, this guy's the first guy who's an actual energy man to run the Department of Energy ever, you know, since its creation in the 70s. So he comes at it from a producer's eye. So he's he's definitely open to things like reclassifying thorium, streamlining some of the regulatory burdens. Uh, you know, uh, I don't need to tell you, you can imagine what, you know, some of the regulatory burdens. So, like, one of the things we would want NRC to do is become a dual mandate. Right now, they're a single mandate agency, right? Safety. That's it. So the NRC theoretically all they care about is safety. But if you only care about safety, then you get 100% safety and 0% innovation, right? So things get locked in 1979. You know, the day the Department of Energy was created was the day innovation stopped. You know, that's why that 1980 date is so, you know, so ominous and looms over us, because it's the day innovation died. And you know, so the dual mandate would be like the FAA. You have to be safe, but you have to promote economic uses of this at the same time. You have to have a balance, you know, just like the Fed. You know, the Fed has the dual mandate of low interest and low unemployment. And how do they balance that? Well, sometimes they have to raise the interest rate, you know, and for, you know, so it's like every other agency has a dual mandate because they know you have to balance that teeter-totter. The NRC is the only single mandate, and we all believe and, you know, have very good evidence that they purposely did that. They knew damn well what they were doing. When you have a single mandate, you know, then that's all you're going to go after, right? You know, and when all you're after is safety, then you are absolutely after no changes, no innovation, you know, no new nothing, you know, just do it the same way you've been doing it. Sorry, that's a little long-winded.
Corin, you're muted, Corin. You have to unmute. I always mute you because you never mute back. So I'm always, it's a dual mandate. Here, I'll ask you to, here, I'm asking you to unmute.
Okay, am I unmuted?
Now you're unmuted.
Yes, I'm unmuted. Okay, very good. Okay, could I just double check? In case if I talk about thorium to someone, they'll say it's some climate denial plot, or you don't understand the radiation risks, or something like that. So, I mean, I understand from you that they use thorium nitrate in mantles on gas lamps for 100 years in lots of big cities. And thorium was used a lot up to 1980. Um, so there's a lot of experience there. So are there people I don't know about who've dropped dead from thorium radiation poisoning? Hello?
Are you asking if people have dropped dead from radiation from thorium?
Well, what is the risk?
Well, the real risk is the same sort of risk profile that a lot of materials have, right? So, like, you don't want to inhale thorium powder, right? It's an alpha emitter,
Mhm.
you know. So if you get it in your lungs, if you get it into your pink, you know, tissue as they call it, you know, your internals, and it's able to be, you know, line to line with your cells, it's the thing that makes it such a good cancer drug, the intense alpha bombardment that it can do with directed delivered, PSA therapy, is that if it's sent into your body randomly, like inhaling the dust, then that's bad news. It's very dangerous. Um, the So that's why, when we handle thorium and, industrially, we try not to handle it as a powder. Two, we obviously wear, a lot of personal protective. We use Geiger counters and other things to make sure that we haven't contaminated anything. So it's like a standard industrial product, like people working with anhydrous ammonia have to be hugely careful, because it's astoundingly poisonous stuff. You know, the precautions you have to take around thorium are certainly no more onerous than that. But in terms of your standard person on the street, you know, if they encounter thorium, which they do every day, it's in a form that's, bound up in a mineral, it's naturally occurring radioactive material. You know, it's been here since the formation of the earth. You've, you've eaten it, you've rubbed up against it, you've been exposed to it every single day of your life. I mean, if you leave your house, that is, or touch a rock, so it's there, it's in the earth's mantle. We've evolved around it. So the the radiation risk is, the radiation risk for thorium in the outside world is vanishingly small, you know, so small as to be immeasurable against, other sources of dangers.
Okay, thank you. Just say you rewire a whole house with aluminium and thorium because it's cheaper and it conducts very well. I just want to double check. Is there any risk from that?
Well, that's probably not a use I would recommend. The first and greatest use for thoriated aluminum or thoriated copper in terms of transmission of electricity would be in trunk lines. That's where you would get your greatest effect. You know,
Mhm.
you wiring your house, one, now you start to, lose your traceability of the material a little bit, because who knows where it is and what part of the house and what houses have it. Whereas transmission lines are the source of 25% of all electricity losses. If we could cut that down in half, that would be a huge benefit to humanity, and it would allow us to get more capacity out of our existing lines. Nothing's harder than putting in a new transmission line. These people who want to electrify everything are, whistling past the graveyard of not in my backyard. Nobody wants more transmission lines, no matter how green they are. And no, I wouldn't recommend, trying to wire out an individual residence or even an apartment complex. The benefit of it would be de minimis, right? You'd have to you have to have something like a transmission line to make it, that's on 24/7, 365 use, to really get, the main benefits from the effects of the thoriated material.
So are a lot of these long
Yeah.
distance transmission lines copper, really?
Yeah, they're copper. They got some steel core in them. The uh, yeah, that's basically it. They're steel and copper.
Huh.
Rarely they use some aluminum. Aluminum transmission lines. You know, just you'd have to use 30% more aluminum to equal the same amount of copper, right?
I see.
Whereas if we thoriated the aluminum, the same amount of aluminum could transmit as much as copper. I mean, that's the point of it. But yeah, so but steel, they'll use steel for strength. They'll use copper for its ability to transmit. And there's obviously, when you look at a core, at a a transmission cable core, there's jackets and everything all over the place.
I'm gonna find someone else to come tell us about small modular reactors. Maybe you know somebody. Pedersen won't do it because he uses the low CO2 of nuclear energy as a selling point, so he doesn't want to talk to us. But maybe someone will. Maybe you can help me find someone. So I won't ask for that. I won't ask for the reactor part. Does anybody else have a
Yeah, and I just want to show you
okay.
what a small transmission cable looks like.
I didn't know there was that much copper. It's a huge amount of copper.
Oh yeah. Yeah, and that's sort of like this is a small cable. You know, this is like a buried cable system, but the big high tension line ones are, they're engineering marvels. Um, but yeah, the most people don't understand we lose about 25 to 40% of all the power we generate just transmitting it from the power station to the end user.
Yeah, right. Okay. All right. Anybody else? Any last questions? Anybody? No. Well, been super fascinating. Corin, quickly.
Yeah, so Mr. Les, sorry, I perjured myself. I went on Slack, but the I'm very interested to know if about the paper you were writing on climate change, and also about vaccine injury. I think that might have been in pilots.
Oh, well, let's save
Can
that
I
for the
look
next
at them?
meeting. We've got John here, and I just want to wrap up the meeting and we can talk about those other things. And you can
Okay.
always check on the Slack. Michael, did you have a question for John?
Yeah, John, what happened to your original client? The
My
guy
original
that,
client,
yeah, the one that got you going on this.
uh, he's still my client. He's a sort of a traditional, engineering client. He's he's a funny guy. He invests in a lot of different industries, and and when we talked about thorium, he wanted to create he got the idea, like he wanted to create an exchange traded fund for thorium. He's like, well, maybe we can get a huge stockpile of thorium and, like, one day it'll become super valuable. And I'm like, you will be playing a very long game there, Cal. so so Cal is still a good friend. Cal is still a good client. And he's still out there, investing in startups and different industries. He's big into miscanthus fiber right now. You guys could look that up. That's a whole interesting area. So he spent about $80 million developing miscanthus fiber industry in the United States. Uh, and but yeah, thanks for asking. Cal is still alive and kicking and good supporter, and he takes credit for everything we've done.
All right. Thank you, John. Really informative. Just a pleasure to have you on. And we also applaud your mission and appreciate your dogged determination to make a difference because that's what it takes. And nobody says thank you. So we say thank you.
Well, thank you right back. I appreciate what you guys are all about, and
Okay.
spread the word if you can. And we're happy to go to thoriumenergyalliance.com if you have any questions. We're here to help
We hope you
anytime you
make
want. Thanks for
progress
the
with Chris Wright.
All right, yeah, with Chris, yeah, absolutely. You know, it should be very good. But
Good.
you know, David, I really appreciate it. We'll talk soon, guys.
All right. Thanks so much. See you
Bye-bye.
next week, everybody. Bye-bye.